collaborative effort between Himpunan Ahli Geofisika Indonesia or Indonesian Association of Geophysicists, or to be short HAGI, and the Faculty of Geoinformation Science and Earth Observation or ITC at the University of Twente. I'm Muhammad Aufaristama, but you can call me Aufar. And it's my pleasure to be your moderator for these engaging sessions. Before we start our sessions, I will invite our president of HAGI, Mr. Randi Chandronegoro, to open the sessions. And for the Mr. Randi, please.
Okay, Mas Aufaristama, are you quite clear? Hear me?
Yes, I can quite hear you.
Okay. Okay, good afternoon, everybody. So, of course, first of all, we from HAGI would like to thank our guest here, Professor Dr. Mark van der Meijde. Am I spell it correctly, Prof?
Yes, that's close enough. Thank you very much.
Okay, thank you. And also our colleague also, Dr. Muhammad Aufaristama from the University of Twente, yeah. Also, maybe I spell it correctly, yeah.
Yes.
And also all of our colleagues here, I see Kang Irwan, yeah, Dr. Irwan from Universitas Pajajaran who sponsor for this event also. And everybody who are able to attend this webinar, which will be discussing about our seismic hazard and also geothermal exploration. So thank you everybody for joining us today. Hopefully later on we will have more attendees on this webinar, yeah, because usually in Indonesia we quite slow in this kind of webinar for the attendees to come. Just would like to talking about our seismic hazard, yeah, because this is one of the subject for this afternoon webinar. Maybe this is quite familiar with our geophysicists in Indonesia. This is because of that Indonesia unique geographical position, which is located in the Ring of Fire. Yeah, I always remember that the statement from a senior of BMKG, an agency in Indonesia that dealing with this subject, several years ago, that this is the one of the main reason that maybe why Indonesia can be called as a supermarket of disaster. Yeah. So that's why HAGI is certainly one of the parties that must continue to encourage effort to ensure that the natural disaster risk mitigation can be continue to be developed and implemented in a well manner. So in the other subject, we are going to talk about the geothermal exploration. Actually, I was attending the presentation from our Pertamina Vice President on last October, yeah. So based on the presentation made in Pangkal Pinang Joint Convention, actually she presented quite interesting information that Indonesia has a geothermal potential of 23 gigawatts, but actually currently our Pertamina just reached and moving towards of approximately 1 gigawatt. So we have quite a lot of potential to catch up in the future. And of course, we need to support also from all parties that the geothermal potential can become greater and can be utilized. Again, this is also to support our government goal to support a zero emission objective on 2060s. So HAGI certainly has an interest in always supporting the promotion of increasing geothermal as one of the renewable energy in Indonesia. And this webinar is one of HAGI's steps to support this. And so once again, HAGI would like to thank Professor Dr. Mark van der Meijde and also Dr. Muhammad Aufaristama from University of the Twente, and hope we can get a very good information from this sharing discussion for this today. Okay, I believe that's it from me, and go back to you again, Mas Aufaristama. Thank you. Thank you, Prof.
Thank you very much for Mr. Randi. So as mentioned earlier before, in today's topic, we will explore into an exciting subject. Like Mr. Randi mentioned, the title is What Earthquake Can Reveal About Earth Structure and Dynamic, Example for Seismic Hazard and Geothermal Exploration. In this subject, we are going to explore how studying earthquakes help us understand the Earth better, especially in predicting risks and finding a renewable energy source like a geothermal energy. And I'm honored to introduce our special speaker for today, Professor Dr. Mark van der Meijde. So as a background of Professor Mark, Professor Mark holding an MSc degree from Utrecht University in Netherlands, and a PhD from the ETH Zurich in Switzerland. His professional journey is marked by contribution to various institutions. He has worked with the Dutch Seismological Institute, or KNMI, and Geological Survey of Netherlands, TNO. And further broadening his experience, Professor van der Meijde has also worked with the Brazilian Seismological Survey and the University of Sao Paulo in Brazil. And currently, Professor Mark is a professor in the Earth Structure and Dynamics at the University of Twente in the Faculty of ITC. And he also, as the head of department of our department, is Department of Applied Earth Science. And his extensive experience and profound knowledge in the field of geophysics, particularly in seismology, make him a great expert on today's topic. So we have more or less 45 minutes presentation and 15 minutes question and answers. As we listen to Professor Mark, I encourage all attendees to think if you have some questions later on in the question and answer sessions. Now, I would like to hand it over to you, Mark.
Thank you very much, Alvar. Thank you very much for the invitation to speak to such a broad audience. I like the wording of the president of HAGI on the supermarket of hazards in Indonesia.
Yeah.
And although I'm today talking about different topics, I think actually Indonesia would be one of the few countries in the world where actually these two kind of studies could actually come together in one topic. So maybe that's a goal for the future to bring all this research together in one location in Indonesia to show really how different aspects of ground motion actually can come together in understanding the Earth better. For today, I've chosen for two different areas. We move for the seismic hazard a bit into the Himalaya region, and the geothermal exploration we move into Africa, into Kenya. A lot of this work has been done as a group effort with lots of PhD students and colleagues in the department. So the most key the key contributors are indicated here. I've already said all this work has been done in the Department of Applied Earth Sciences at ITC in the Netherlands. ITC is a remote sensing institute with different fields of expertise. We are covering the applied earth sciences part. We have around 70 people in the department with staff, visitors, postdocs, PhDs. Next to that, we have our MSc and other students running around. So it's quite a sizable group of people working on all kinds of topics. We focus mainly on two earth science domains. One is the natural hazards and disasters, so that's the first part of the talk for today. And the geological remote sensing and geophysics is the second part. If you would like to see a bit more, I provided the webpage for the department so that you can see a bit more what we are doing, because there is much more to tell, but we're not here to talk about the department. We're here to talk about earthquakes and particularly the different roles that they can have. I think earthquakes are mostly widely known for the disastrous effects. They cause damage, they cause problems. We see them a lot in the news, but what we do not so often see in the news is what we can actually do with the data that comes after an earthquake. So there is often damage that is happening after an earthquake, and then it's widely in the news. But we can use the earthquake signals or the ground motion basically also in different ways. So we can use it actually for assessing future seismic hazards by doing advanced modeling techniques, looking at a different way of our earthquake signals, combining it, especially for the first part, with remote sensing efforts. We actually have a tool that we can use to predict how seismic hazard will look like, particularly in mountainous regions. On the other hand, and that's the second part of the talk, is that the ground motion itself travels through the Earth, and we have basically no means of touching that part of the Earth. So our main source of information comes from seismic waves that travel through the Earth. And by carefully looking into the behavior of these seismic waves, we can actually get a better understanding of Earth structure, which in the presentation that I will give today will link to geothermal exploration. So let's kick off with topic number one, seismic hazard, and how we can use earthquakes better to understand seismic hazard. There is a significant remote sensing component in there. I talk basically on two earthquakes. One is in Kashmir, the other one is in Nepal. But to fully understand the total of the story, we start off with a bit of remote sensing and how we came to this research and how we have built this research up by combining all kinds of different data sets to get to a final picture. So one of the challenges that we have is that the seismic waves that travel through the Earth are basically a bit non-unique. There could be different solutions that can all explain the behavior of the seismic waves. So what you have on the other side is that you have what is happening at the surface, because that is a unique observation that we have as a result of the seismic signals. So one of the challenges that we have in there is that what we observe at the surface, we can often observe in high resolution. Centimeters for visual. On topography, for example, we can go down to 15 or 30 meters. But our seismic waves are normally at a much different scale. Our earthquakes are at a much different scale. They are kilometer scale or hundreds of meters. And the total area affected by an earthquake might be easily 75 by 75 kilometers or even bigger if you have larger earthquakes. So one of the things that we need to do is figure out how can we use these different scales and how do we match them together. So data from Earth observation satellites, all kind of constellations, is increasingly being used also to help studying the Earth's interior, its surface and its atmosphere. But particularly the link between surface and interior is an interesting one because it can help us understanding better what is inside the Earth and help in the imaging of the Earth's composition and structure. This gives a very complete spatial coverage compared to only field-based studies with seismometers that have a few added points here and there, but then we don't have any further information. So to use this kind of information can be really an added value to add information, particularly for data scarce regions where we have just a limitation of availability of sensors, or like in Indonesia, where would you start measuring? There is so many things that you can measure and you cannot cover the whole country with sensors. So these kind of data sets can help in understanding what is happening in between. But we have all heard the saying, especially those that have a link with remote sensing. Remote sensing is a powerful tool for, and then fill in whatever it is powerful for. But it's very important to realize that it is also a limitation. We only see a small part of what the total picture. So we only see a part of the solid Earth. So it's either the surface with optical or hyperspectral remote sensing or radar, or when we go more into geophysical sensors as part of the remote sensing community, then you get often a bulk value that covers a larger volume. So we need to be careful on how we use it and how we integrate this with earth science knowledge. So that brings me immediately to the first case study that I would like to talk you through. And this work is done by a couple of years ago. It was the start of our trajectory into this field. And we focus here on the earthquake that happened in Muzaffarabad, the Kashmir earthquake. And let me put on a pointer there. So we are here in northern Pakistan, and there was a large magnitude earthquake, 7.6, I believe, if it's correct, was happening here in northern Pakistan, in the Himalayas. And what we have seen there are very peculiar patterns of damage that very strongly link to the effect of topography. So we wanted to look a bit further in detail in there, because the topography in these cases can really lead to an amplification of seismic signals by trapping energy. And that has also secondary effects like landslides, which is the field where we are now strongly moving into, really trying to link, if you can not only look at the earthquake, but also look at the secondary effects, so the earthquake-induced landslides. We save that for another part. I will focus today only on the geophysical components. But we see here a topographic model from remote sensing, quite high resolution. And what we were wondering about, can we actually model the effect of the topography if we carefully simulate this whole environment, not only the subsurface, but also the surface topography? So normally we skip that a bit, but in this case, this was our specific thing. So we looked into the differences and the effect of resolution of data and the way you model it. So our best model was a digital elevation model at 30-meter resolution. And you see here that we keep on the vertical columns, we keep the resolution always at 30 meters, but we modeled it with different resolutions. So here we have a model that is at 90 meters. This is at 270, 540, and around a kilometer. And we are interested in what kind of output that we then get in the modeling is still realistic with the lowest resolution that we can use. Because if we go to 30-meter and 30-meter model, forget it, you will not be able to model this very easily, because it will explode on your computer if you would like to do that on a 75 by 75 kilometer model that goes 40, 50 kilometers deep. So we would like to test the optimal balance. And we have used here 1 kilometer also, because at the time of this research, a lot of the global models that are looking into earthquake effects use 1 kilometer topography as an estimate for these kind of surface effects. Now, what you already see is that there is a large differences from the high resolution changing through lower resolution in input as well as modeling. And you will see that the detail that you get between the lowest resolutions here at the bottom right versus the top left with the highest resolutions is quite different already visually. So we expect that this will also have quite a bit of an impact on the seismic waves that we are using. But the seismic waves are covering a somewhat larger region. So we are particularly curious to see, like, okay, is this indeed as bad as we hypothesize that it is? But maybe we don't need to use the 30 meters, and we can actually go a bit lower because of the frequency content of the seismic waves. That is not so sensitive to the smaller scale features. So what we did is, this is basically the same as you have seen before, but now we do a comparison between the real model versus the modeled model. So this is the real model with 30 meters and 90-meter resolution model. And then we are trying to see how the seismic signals, how the signals look like when you start comparing them. And there it is quite interesting to see that if we look, for example, here at the 540-meter resolution models, that in the meshes, that it actually doesn't look very nice. It should be lining up along the red line over here. Now we see that the averages are already offset. They make different angles, but particularly this is a big cloud. And we would like to see that it becomes more a bit very, very small. We also see that if we decrease our input to very low resolutions, that we somehow still stick to it, at least towards the trends, but that we are shifting away from the actual model. So we start to underestimate the effect and the comparison with reality. So the central part here is the part where we said, like, okay, somewhere in here is the solution that we are looking for, that we would like to investigate a bit. And we said, like, okay, what would be the optimal resolution that we can use, that we can make it efficient in computing, but we're still realistic in our output. So we look particularly at the 90 meters and 270 meter DEM resolutions, and then the meshes. This is our model and the resolution of the model. And we compare basically in ratios along these lines. This is the output of the comparison of those two. This is the output of the comparison of this one. output of comparison of this one, and the cross one is over here. Now we see particularly that these models, so the comparison from here to there, are relatively neutral in the variation, the ratio. So they are very bluish. The more they are bluish, that's fine. If it becomes a bit reddish, we have deviation. So we're under or overestimating. So what we basically see is that changes in DEM resolution make quite a bit of difference, but the changes in the mesh resolution do not. So the best option that we probably have is that we stick to a reasonably high resolution input, but we model it at lower resolutions. That will give us still quite an estimate that is pretty okay. So we can go to a high resolution DEM, but we can go coarse in the modeling, and that is the best representation that we can have. So this is now our starting input for our study. So now we know how we need to model the terrain. We have used a uniform model for the Earth structure and composition based on global models. And then we come a bit to our approach for the seismic hazard. So what we can now do is that we have a realistic environment that is accurately simulating seismic wave propagation, but also accurately simulating the effects that we have at the surface. So for the seismic hazard in this area, instead of only looking at this earthquake and its effects, we are basically picking 25 different potential locations of earthquakes. They all run along the main faults that are in the area. We have homogeneously distributed them through the area. So basically an earthquake can happen at any of those locations. And we model the effect of all these different events. And we already see there is quite a bit of topography differences in there for almost 4,000 meters in elevation differences between some flat parts in the valleys and on some of the plateaus. And then the high mountains that we see that are steeply going up from the valleys, peaking up at 4,000 meters and higher. So we have massive topography, it's very irregular. We see all the ridges running in and out of the valleys. So it is quite a complex terrain. So now let's see how this looks like. So these are the 25 models. The top one here is the original event that we have, and then we have 24 other simulations, all possible realistic events that are based on a realistic source mechanism for this area. And we can clearly see that there are strong effects of the topography, because in principle, for all these earthquakes, the radiation pattern is the same. But we can clearly see that for this one and for this one, there are completely different radiation patterns. We see the same over here. As soon as that we move a bit into a different direction, quite a different pattern of interaction of the seismic wave at the surface occur. So we see clearly the effect of topography in this kind of effects, in this kind of modeling. That also means that depending on where an earthquake happens, and if you're on one side or another side of a mountain, you already see that there is quite a big difference in how you might experience the effects of an earthquake. So what we did is we basically calculated the mean peak ground displacements based on all these scenarios. And we see that some areas are definitely much more exposed than other regions. They experience potentially average peak ground displacements that are relatively high here on the plateaus and also down in the valley. So we clearly see the effect of the rivers and the valley basins. But then we also look at what is the standard deviation of this average out of the 25 different realizations that we have calculated. And there we see a somewhat different pattern. So let me highlight a few areas for you. This part, for example, is very high in mean peak ground displacement, but it hardly shows any variation in all the realizations that we have. So this area is overall all the time highly exposed to high peak ground displacements. If we look a bit north to that area, we see the other part over here, which is clearly lower in amplitudes than this area. but the standard deviation is much higher. So we have certain earthquakes based on certain directions and interaction with the terrain will give you very high peak ground displacements, but there are also earthquakes that will not have so much effect into this area. And we see a bit of a reverse effect over here, somewhat in between peaks, but also here low standard deviation. So we know that we are here at a somewhat more intermediate level. This one is very low in the peak, in the mean, but there is a large variation. So some events have a lot of impact, other events do not have a lot of impact. So we have combined that into the final hazard map, where we say like, okay, anything that goes into low and medium is then in the more yellow and greenish colors, and the more high and whitish it becomes. So with a bit of UE over it, there is a very high seismic hazard risk based for this specific area, based on interactions with the topography, so specifically for this particular area. Now, if you combine that with the topography, we clearly see some of the topographic features coming into detail. So we can have, this is absolute value. So this is about absolute effect of the ground motion for a specific area. But we can also look a bit into more detail. What is now the distinct topographic contribution to this? So we have done all the modeling again, and for each of the earthquakes, we have also modeled when we have taken the topography out. So we have taken a flat model that is basically the seismic signal that comes in at the bottom of the topography, and we have compared that with the signal that we got out of the 25 realizations with topography. So this is the topography. This is then the mean peak ground displacement differences. So we see that for the blue parts, there is a de-amplification because of the topography. For the reddish part, there is an amplification effect of the topography. And if you then compare that, we see that all these kind of ridges that you see coming out here that are sticking out in the terrain are actually capturing all the energy. And we see that we have almost a meter of additional amplified peak ground displacement for these kind of areas. And we can do the same again for the standard deviation. And then you get very clear patterns that these higher mountains here in between the faults, they are being exposed from both sides to earthquake activity, have experienced very strong enhancement of the seismic signal. So we see here that we have a large standard deviation, so large variability, depending if an earthquake comes from the left side or from the right side. So we clearly see here for our seismic hazard understanding that there is a strong variability in seismic hazard throughout an area, but we also see that it is very strongly controlled by topographic and amplification effects in the area. So this will help you in your planning for now, where can you expect what kind of ground motion and under which conditions. And then the earthquake in Nepal happened. And we did here some forward modeling. So we basically started and say like, okay, we started off with an event, and then we start looking like, okay, we take other events. So how does it look like what we are doing? So we modeled the process and we observed the effect. In the Nepal earthquake, we were actually triggered by the effect. So what it was that there was a bit of a funny earthquake there, which was large in magnitude, but it didn't trigger so much damage and landslides in the area. So what we did here, we basically observe a signal, and by the modeling, we try to learn more of the process. So we start off with the observations. So the issue was with the Nepal earthquake, and it reached all over the news from both scientific organizations, but also newspapers, that the Nepal earthquake was less catastrophic than expected. Level of damages is lower, lessened impact, less intense than feared, based on the magnitude of the earthquake. It doesn't mean that there was no damage, there was significant damage, but for the intensity of the earthquake, it was actually much less than expected. So this triggered our question like, okay, what happened? Because it all didn't look that well. It was a big magnitude earthquake. This was the radiation pattern. So it started off here. And this is the profile along this line. And you see that the highest intensity was actually taking place here, relatively close to the city of Kathmandu. But Kathmandu did not have that much damage, despite that all conditions are present for massive problems. So you have a big magnitude earthquake, and the highest energy release was pretty close to the biggest city in the whole area. So we had little damage. People did some studies. There was little effect of sediments in the area, contrary to what was expected. So there were many studies, but not really a conclusion yet on why did this earthquake it was not much more destructive. And one of the 5 factors that was not studied, and we were just wrapping up our previous study, was the effect of topography. And we thought like, well, it is a mountainous region. Let's have a look at it if nobody has done it yet. So there are basically 2 mountain ranges in between the fault that was running over here, and we see this mountain range and we see this mountain range. So this is a view from Kathmandu going over the first, and behind that the second mountain range, and then these big peaks you see here in the background. So the earthquake was happening basically behind the mountain range that you just see behind here. And we see that this is a relatively flat area. It's in the sedimentary basin, but we have all this topography in between. So this was the mesh that we have created. We followed here exactly the same procedure because it is a similar kind of topographic setting, same topographic differences. So we said, okay, this is our model. This is the basin area. The earthquake was over here from a top point with topography on it. Here was the fault line running, this was the rupture path, and here was the highest energy release moment. So you see it's almost as close to the city as possible. Then we did 2 things. So we looked again at a model that has no topography. So we took this top layer, we took it off, and then we looked into the model that had topography. So that is with the layer on. And you can clearly see the effect of the topography, which is changing the whole pattern of observations of where energy is going and how it looks like. So it becomes from a relatively smooth field just coming up out of the earth, it changes into a very irregular pattern. So to understand exactly the effect of the topography in the next figures, we will basically look at the ratio image between the one with topography versus the one without topography. So it's highlighting the effect of topography alone. So we're not looking at absolute values anymore. So this is then that ratio image that we also showed for the Pakistan earthquake. So the red parts are amplified areas, the blue parts are facing de-amplification, and the white parts are basically not really a change in signal between model without and with topography. And what we clearly see here is that this is a relatively uniform pattern. We see some of the effects of the topography, but by the topographic elevated areas over here, those mountain ranges, they are actually positioned in such a way that we see that the valley is basically shielded by this, and a lot of the energy was moving just along the sides of the basin area. So the red part here is the highly densely populated area, and in the black line is the outline of the larger Kathmandu Valley. So we see that there was an energy release that basically just skipped the basin structure, which was deflected from this part coming down and then diverted into the sides where we see here strongly amplified signals, stronger than what was expected without topography. But the area here is mainly whitish and bluish, except for this small ridge that is running here in the middle, which is a topographic high in the valley area. So we see that we have basically see here a lessened effect of the earthquake simply because of the topography. And then we got a bit curious because this looked, of course, fantastic. This is like a topography could be explaining it. So we were wondering if we would now move this earthquake a bit around and we go to areas of the second and the third highest energy release. How would it look like then? Was Kathmandu indeed lucky, or what are we looking at here? What is the role of topography? Now, to understand that first, we had one observation that said like, okay, we would like to see, is this actually a real signal? Is it realistic? So we had in black an observed seismic signal for the area, and in the red line is our modeled signal. And we see very clearly that both in amplitude and phases and frequencies, this observation that we have modeled fit actually very, very well, considering that we use a relatively simple model and we have not included sediments. So the variation here is probably due to smaller scale local features that we have not taken up into our relatively simple model, only looking at topography. So that gave us some confidence. Let's look at the other models. So we took, originally it was over here. So we took a source location over here, we took one over there, one over here, and one on there. So we moved to both sides of the main energy release that we had. If we then look at the amplified areas, we see that if the earthquake energy release would have happened a bit earlier along the fault, so the maximum energy release would have been here, we see that the area of Kathmandu, and particularly the populated area, is massively amplified in peak ground displacement. If we then move a bit to the other side, we see that, for example, for an earthquake that would have happened here, the southern part of the densely populated area would have seen a lot of increased exposure. We actually see here the highest values of peak ground amplification in all the models that we have done. And if you move it completely out of here, we still see that the northern part still gets more exposure or more peak ground amplification than in the model that we had, which was most nearby. So we see very clear here the effect of topography and how topography can actually tunnel the energy into a specific direction, leading to very strongly enhanced seismic intensity at specific locations. This also gives a bit of worry for future earthquakes in the area, because apparently Kathmandu was really lucky that it happened here in the central part. Any earthquakes that might be happening in the future along this path, but just a bit away, are likely to have a much bigger impact. So Kathmandu is likely to become more exposed in the next earthquake than it was in this one, where the topography really helped to shield Kathmandu from massive shaking. Now, we did some very quick analysis also linking to damages in the area. So all the points here are point observations or cumulative point observations for the for populated areas and the damage that was observed in these areas. We see that we have in the green parts are the ones that actually coincide. The red ones are not. And then we have a few that are in between here from another data set which also coincide. If we then look at the amplification that was based on our modeling, then we see that in the areas where there was no damage, we see indeed low amplification values. And that is slowly going up to moderate to severe damage in houses and houses that were destroyed, which are falling mostly into the category of mostly amplified areas, purely due to topography. So the sediment effect is not taken into account here. And we see that already only this kind of modeling can already explain about 2/3 of the damages that we have observed in the area. So that was a bit of a part where we say like, okay, how can we use earthquakes to understand our risk better, and how we can use earthquakes to do a modeling of how things could also look like if in case there will be another earthquake at another location at another moment in time. I would now like to twist basically the mirror around and say like, well, how can we actually use ground shaking to understand the earth better for actually helping us to become a better world, instead of it's only from a more destructive part. So one of the things that we have been doing is looking into very small seismological networks to understand better Earth structure and composition and dynamics. And one of the parts where we have done that was in the Olkaria geothermal field in Kenya, where we would like to try to understand the geothermal motor, the mechanism of a geothermal field a bit better. Now, there is a lot of geothermal potential in Kenya. So this is the eastern part of Africa. Kenya is over here, Ethiopia and Tanzania south of that. And in the red lines, we see the East African rift system, which is an intracontinental rift system. So the Earth is slowly being pulled apart over there, and warm mantle material is coming up to the surface or close to the surface. And that gives a very high temperature gradient in the surface and a real source for heat. Now there are different segments over here, and we are focusing basically on the part that is over here, which you see a bit in more detail. And we see here the extension of the East African rift part. We see a lot of volcanic activity in the area, so there are a lot of volcanic centers. We also see that it is a deeper part with some of the lakes, with some of the volcanic activity still underneath it. So this is the part where the crust is most thin and the heat of the deeper earth is coming most close to the surface. In the middle of that area, here is the capital Nairobi. We have here the Olkaria volcanic system, very close to the big Longonot earthquake system, and north of that is Lake Navasha, a small lake here, so it's one of the lower points. They have been using geothermal energy in Kenya already since 1981, and Olkaria was one of the first fields that was being used. So this is the area. You see there is here is the top part of the Rift Valley, and we're here down in the Rift Valley, and this is the Olkaria system. So there are a few domes coming up. There are some recent lava fields also in this area. There is running a big gorge running in between of those, so it's an additional extensional system. And our key interest in this area, in this study and we are focusing here on the red part, is where are the fluids, where are the fluid paths, where are the heat sources, and can we actually visualize, by studying this in detail, how all these fluid paths and heat sources are actually moving around, from going down with the cold fluids that we are pumping up, and then the heat from the geothermal motor, the engine, coming up. And can we then, if we understand this a bit better, can we then identify new areas for geothermal expansion and development? So this is already operational since 1981. It's continued in operations. There are some recent extensions in this part, and that's also why we covered both the existing part. We would like to see what the role is of this extensional gorge, this fault system that is running in between. Is there any link between the left and the right-hand side? And can we assist in developing this part further based on our studies? So the geothermal motor concept is in this case based on a high enthalpy magmatic heat source. So we have magmatic bodies intrusive that are coming up from larger depth. We have those fingers of warm material coming up, those intrusives, and those are leading to increased heat flux towards the surface. The whole system is sealed by a cap rock, so we see that it's trapped basically in this domain. And we would like to know, like, okay, when it's going down again, where does that happen? Or when we inject it, what will happen with those fluids? So we're basically looking at the circular motion, this convection within the reservoir, which is basically the running engine of a geothermal motor. So we have installed a seismological network there. We installed quite a few seismometers. Most of them were dug into the ground. There were a lot of loose volcanic sediments on top of it. So we first dug a hole to about 1 meter deep, and then we drilled into the more solid ground for a good coupling of the seismometers. We drilled with an engine drill We drilled a hole of about 20 centimeters wide, about 1 meter further deep. So the seismometers are about 2 meters under the ground. We then put the seismometer in, and these are nice seismometers that we can just, they don't need any massive infrastructure. You can just put them into the ground. You put them horizontal, you orient them towards the north direction, so we have full control of the 3-dimensional wave field that comes in. Then we close the hole, solar panel goes on top of it, and a few meters away from it to not disturb it when we are surfacing. There is the data locker in a small house. And that was basically the setup that we had in the Bulgaria area. So these are all the seismometers that we have installed. So we are with 6 seismometers on the side of the already running field. We have a good coverage of this gorge that runs in between, and the other stations are on the newly developed area. We are looking here not really into the traditional earthquake data, so we're not looking here at data that is originating from earthquakes, but we're looking here at seismic motion that happens in the region or outside, but that is creating background noise. So this is basically the noise that if you study an earthquake, you want to get rid of. But in this case, we want to get rid of the earthquake signals, and we are only looking here at the continuous motion. And that are background vibrations traveling between stations. Could be from anthropogenic noise, is partly based on ocean motion. But the Earth is in continuous motion, and we try to use that continuous motion to understand the structure that is happening, what is happening in here. So what we are looking is that we try to understand what happens between 2 stations. So we have here 2 stations that we are using, and we look at the distance versus the delay of seismic waves between areas. So basically what we are doing is we say, okay, we know what we record at one station. If we then also record at the other station and we compare it, we can actually understand, see how the velocity of those waves are changing with different frequencies that we are using. And then you get pictures like this that show you very clearly here with a white line the most dominant energy releases, the most dominant phases that are traveling for each of the frequencies, each of the periods, and at which velocity that they are doing that. So we base that on many observations. So this is an average of hundreds of observations, and this is then the final result. So we do this for all these black lines that you see here in the model. So we have long paths, we have very short paths, but the main thing is that they are all crossing each other. So we get that we can actually separate the whole area in an inversion process into smaller blocks that will that will each have its own unique velocity contribution to the whole model. Now, then the question is, what is then the best resolution to do this? And that depends a bit on the stations that we have and the frequencies that we are using. So we created, to test this, we created an artificial subsurface structure of very high resolution of 0.005 degrees. So that is 500 meter resolution. And that goes up to 0.01, which is about 10, 11 kilometers resolution. Then we simulate the information from the network. So we look at which waves and paths do we have, and we see what we can actually resolve. So the goal is to retrieve the same checkerboard features that we put in and see where we can actually retrieve that. And the areas where we believe that we can retrieve it well are highlighted by the black line. And then you see that if you go to the very high resolution, we only have in a part of the whole area, we have a good resolution, but most of the area is all smeared out, and we cannot uniquely say like, okay, at this location, the velocity is this. That improves a bit when we make it a bit more coarse. And at a certain moment, we see like, okay, here we have actually over the whole area in our network for basically all the stations and the data in between, we have a pretty good retrieval of the input structure that we have. When we go even more coarse, it's not getting better. But this one is covering a much larger area than the one, the somewhat more higher resolution. So this is our preferred resolution at about 800 meters resolution that we are using to model the subsurface. And then we make velocity models. So we have a velocity model based on all these kind of different measurements that we have done. We do run an inversion that each of the locations in the model, both in space and in depth, so laterally and in depth, gets a unique assignment of velocity based on the observations that we have. And we see quite a bit in there. So these are horizontal slices through the model from 0.1 kilometer to 5.0 kilometer, with small steps at the top and what half a kilometer steps at the bottom. And we see for the shallow features, we very clearly see features like faults that are running over here. We see the gorge structure very well, and we already see that the left side and the right-hand side are looking somewhat similar, at particular or different at this case, particularly at the shallow depths. At the larger depths, it looks a bit more homogeneous again. When we go to half a kilometer or 0.8, 0.7. So these are then areas where we see the cap rock of the geothermal reservoir. So there is more homogeneity throughout the whole area, and this, because of the sealing behavior of the clays, it closes the effect of the faults that we still see at the surface and also see coming back a bit more at depth. But we see clearly here all these kind of features in the top layers. Now, we also see very clearly increased, so low velocities over here, which are normally indicative of sometimes more warm or more wet, or both leading to lower velocities for a certain area. But we also see places where we have more relatively faster velocities, where the soil is, the ground is more compact, is probably a bit drier. For example, in a sealing layer where you do not expect that any should be really dense and there should be no water in there. So at larger depth, we still see that we have quite an interesting feature running here in the direction of the dominant fault lines in the area, where we see a bit of a concentration of low velocities, indicative potentially of warmer temperatures, maybe more fluids, but it is always not uniquely resolved. There are multiple possible solutions for the same feature that we see. So we have tried to add some geology in there. And we see definitely some indications for thermal upwelling in our model. If we look into the part where, yeah, there it goes. When we look into the velocity models for the vertical slices, we take a few slices throughout the model, and we see actually what we can try to find out. And if we, for example, look at the E and E prime, that's the model down here. We see here that the gorge is running, and we see that the gorge has a very distinct effect in our velocity model. We clearly see the clay cap here on top. We see a first reservoir layer, and we see a second reservoir layer, and we know that those both exist from the drilling in the area. And we also see the different drilling borehole locations over here. And there you can already see, and this is also confirmed by observations, that, for example, this one is not the most successful drilling that there is. And we see some very clear anomalies that might be much more interesting for favorable regions for drilling and thermal indicators of thermal upwelling. The two layers with low velocity, so those are more the yellowish reddish colors, seem to be reservoirs of geothermal heat that you can potentially put into, but we also see that spatially these reservoirs are not continuous. So there are elements in there that definitely show some other features where we have much higher velocities, potentially looking at areas that have another kind of dynamics or another kind of composition. So this is the final geothermal reservoir model. We see the same features in there, the cap rock. So this is our 3D model of the whole area. We see the intermediate reservoir, we see the deep reservoir over here. So this model runs to a few kilometers. There is an intermediate over here. So we have the upper, the middle, and the deeper part. We see all these vertical fingers coming up. And if we now link this one then to the geothermal motor conceptual model that we had, we see that there is a remarkable similarity between the final and the conceptual model. So these kind of magmatic bodies and intrusives, we see clearly coming up here in the model as well. We see that we have these reservoirs and these intermediate sealing layers that are there. And we also see that this variability of motion into such a reservoir because of the flows is clearly visible also in the velocity structure that we have modeled. So by using ground motion data, continuous shaking motion data of the Earth, we can actually, even on a very small scale, because this whole area is about 10 by 10 kilometers only, we can actually get a very good insight into the velocity structure, which helps us into understanding such systems better. So the take-home message after this presentation is that ground motion basically has two phases. The ugly one is the earthquakes and the damage that it creates. But the pretty one is that all this ground motion gives us very useful, valuable data to provide unique insights into processes in earth structure and composition. It allows us to look into new ways of looking into seismic assets where we do not have to wait before an earthquake occurs to understand how the effect might be. So particularly on areas where you have little seismic hazard or occasional earthquakes, but you expect that there will be more, you can actually start simulating real data. So not only on statistics, but this is based on real data that we can actually validate to some of the earthquakes and assess the reliability for future earthquakes. So we can assess seismic hazards for future use. Also in the subsurface, because the small-scale seismological networks are providing detailed views on geothermal magmatic systems. But if you would like to start an exploration in a certain area, you can also use these seismic hazard studies to assess how an area would respond to, for example, an increase of geothermal activity exploitation in an area. So this way we have tools to understand better what the seismic hazard is, but we have also tools based on the same data that will help us in fine-tuning our exploration and exploitation of, for example, geothermal magmatic systems. And with that, I have come to the end and happy to take some questions.
Yeah, okay. Thank you very much, Mark, for that insightful presentation. Now we'll move into question and answer. Please feel free to submit your question through the chat features or direct questions to Mark. I have one in the question and answer box, but I'll let you first in the live questions. If not, I will see in the chat box. There's questions from, I'll read it for you, Mark, from Mr. Kadek Palgunadi. And thank you, Professor Mark, for your presentation. It was so insightful and interesting. I have a question related to the topographic versus basin effect to the ground motion and hence hazard calculation. I wonder what makes the seismic waves do not trap in the basin, which results in higher ground shaking on the mountainous region. In addition to that, have you compared which effect is more pronounced, basin or topographic effect? I'm still unclear, do you use 3D or 1D layer velocity models?
No, there are a few questions in one. Let's kick off at the top. Sediments will definitely have an effect. But the challenge is that variations in sediment thickness are at a much smaller scale than topography and the seismic wave field variations. So if you would like to do this kind of modeling and go to high resolution models at the top of these meshes, it will require much stronger computers than what we had at our disposal. It also relies that you have accurate information on the sediments, and that is something that is often missing. And then, yeah, you would have to guess. We can do that, but yeah, then it's a bit difficult to assess what would be the actual real effect of these kind of things. So basically, we lack a bit of information in many places to include the sediment basins properly. So that also means that we haven't really compared which effect is more pronounced, the basin or the topographic effect. We know for Kathmandu that based on some studies that they have done, they say like, well, the basin effect there was small, which would also make sense because if we look at our data, we see that there is relatively little data energy going into the basin. So therefore, there was also to be expected that the effect was a bit less. There is still a factor on the frequency content of the waves that are going in, which was supposedly a bit on the dominant on the low frequency side, which helped to avoid interactions on the small scale basin features, which would be more sensitive to high frequency variations in the seismic field. In our case, we used a 1D layered velocity model because for Nepal, there is no high resolution subsurface velocity model available. So we just used a global model. But that global model has a resolution of about 100 kilometers. So the whole study area fell into one pixel of that model. So we have just used an homogeneous 1D layered model for that area.
Okay, any other questions? Yeah. Mr. Kadek, you have more questions?
Thank you. Can you hear my?
Yes,
my?
you can.
Yes.
Yeah.
Yeah. Thank you for your answer, Professor Mark. It was very clear for me. So I have another question related to the ambient noise tomography that you showed at the end. So I wonder if the resolution with the depth is almost similar with the resolution with the horizontal resolutions, and how would you ensure that the interpretation in the depth is quite robust? Thank you.
Yeah, we expect that in the vertical resolution, we are actually doing a bit better, simply because of the sensitivity of the dispersion curves and the range of frequencies that we are using, which is relatively high frequency. So we're using relatively small. The spatial is dependent on the distance between the stations, and we cannot do much about that. Validation is in this case, and I haven't showed that all in all detail, but we are almost submitting a paper about it, which has all this detail in there. We have looked into a lot of borehole data for this area as well. So all the velocity profiles and all the interpretations have been matched to boreholes from the geothermal exploration, where we know exactly what is what at which depth. So we could actually validate quite a bit of this, but definitely not all. But what we also see is that there was a good correlation between what we observe in our model and how successful certain wells are in terms of energy production. So some that were doing well were indeed in areas that we have marked in our model as less favorable. Some that were doing very well are indeed in areas that are much more favorable. So there are some links into there, but there are also all kind of extra factors that are not very well captured in our model, like, for example, the permeability, the porosity, potential clay content in the water, which might lead to blocking of the geothermal system, which affects to some extent the success of geothermal exploitation, but which is not directly visible in our data. So there is still, you try to solve something that you cannot see. We have used as much as possible all the validation data that we have, and we think we have a pretty good grip on understanding that 3D model that I showed. But yeah, there are still lots of questions remaining, and probably the best way to go forward is using other geophysical data like gravity, magnetotelluric, MT data that will help you providing just the other parameters that we do not capture with seismic motion, but that are very indicative of other factors that play a role in the full understanding of such a geothermal motor system. I hope that answered your question a bit.
Yes, thank you.
Any other questions? Answer box at this moment. So if we don't have a further question, we'll wrap up the session. As we wrap up today's session, I would like to extend our thanks to Mark for his insightful presentations and for all of your active participations. We hope this webinar has offered valuable insight into understanding two phases of ground motion that Mark mentioned earlier, seismic hazard and the exploration of geothermal resources. We also look forward to continue collaboration between HAGI and ITC in the future. And thanks again for joining us today, and we look forward to seeing you at our next event. Thank you very much.
Okay, thank you, Aufar. Thank you, Mark.
Thank you all for attending. It was a pleasure being with you today.
Okay.
And bye, and have a nice weekend.